Okay, hi everyone. So thanks for coming along. So my name is Róisín. I'm an assistant professor at Trinity College Dublin in Ireland. And I've been working on transcranial magnetic stimulation, particularly in motor neuron disease and some other contexts for about 8 years now. So first thing I wanted to say, Zach mentioned it before, but I was just looking to get a flavor of like kind of who's experience level, who's here. So there is a little poll badge in the bottom left. If you could just vote on those, just so I can see kind of what level of detail that I should give. But this is not going to be kind of a webinar on the fundamentals of TMS, but more comparing the threshold tracking and fixed intensity approaches to doing paired pulse TMS. But I will do like a very quick recap on what TMS is to start off for those who haven't any experience with that before. So I will start off with a very quick overview of TMS. So transcranial magnetic stimulation is a non-invasive way of activating the cortex. So we're using magnetic pulses. So we place a coil, usually with this figure of 8 shape, like you can see in the figure here, to deliver these magnetic pulses upon the scalp over the area of the cortex we want to activate, and those magnetic pulses then activate the underlying cortical circuitry to evoke some response. Now, typically we apply TMS most often over the motor cortex, because when we activate the motor circuitry, we get a quantifiable output in the form of a muscle twitch. So what we can do is apply TMS over the motor cortex to activate upper motor neurons. They send action potentials down to the lower motor neurons in the spine. Those in turn activate a specific muscle, which will then twitch. And if we apply electromyography or EMG at the same time as we do the TMS, we can quantify that muscle twitch in the form of a motor evoked potential, or MEP. And the size of that MEP is used as our readout of how responsive the corticospinal tract was to the TMS. So we can apply TMS at different stimulation intensities and map how the size of the response gets bigger for different people. And that's kind of the basis of using TMS to study the motor cortical function and also the corticospinal tract function. There is a more complete workshop on introduction to TMS that Brainbox do, if you want kind of a more detailed introduction than that. But if I just kind of add in some terms here, if we refer to this pulse that we're applying, which activates the corticospinal tract and then causes this motor evoked potential, if we call that the test pulse or the test stimulus, what we can do is apply another pulse with that test pulse. So that's when we do so-called paired pulse TMS. So what we do is, as well as the test pulse, which evokes this MEP or motor evoked potential, we add in a conditioning stimulus, usually before the test stimulus, with a very short interval, which we call the interstimulus interval in between. So depending on what interstimulus interval we use and where we give the conditioning stimulus and how intense or the intensity of the stimulus that we use for conditioning, we find that we have different effects. So what the conditioning stimulus is designed to do is activate some other aspect of the motor cortical circuitry, which regulates the upper motor neurons, so that when we then deliver the test stimulus, the conditioning stimulus has either caused the upper motor neurons to be more or less excitable. And as a result, then when we deliver the test stimulus, we see a smaller or a bigger response to that stimulus in the form of a bigger or smaller MEP than if we hadn't had the conditioning stimulus present. And that's a bit confusing. I'll go through it a bit more in a second. But in short, various research over the last, I guess now it's almost 40 years, has shown that depending on which interval you use between the pulses and where you give the conditioning stimulus and how strong it is, you can activate different known aspects of the circuitry. And I won't get through all of those now, but for this webinar, I'm just going to point out one example of such a phenomenon, which is called short interval intracortical inhibition, or SICI. So in the case of SICI, what we do is we apply a conditioning stimulus between 1 and 5 milliseconds before we give the test stimulus. And what we see is that when we have the conditioning stimulus there before the test stimulus, the response, the MEP on average, is smaller than if there was no conditioning stimulus. So we are inferring that the conditioning stimulus has activated some inhibitory aspect of the circuitry, which is dampening down the excitability of the upper motor neurons so that they're less responsive. Now, various pharmacological studies and other types of studies have indicated that actually within that window of using 1, 2, 3, 4, or 5 milliseconds, there's actually inhibition caused by different physiology. So it seems like when we use on the lower end of that scale, so about 1 millisecond, we are measuring or what we're eliciting is inhibition that's to do with the extracellular tonic GABAergic activity. Whereas if we're looking at an interstimulus interval of about 2-3 milliseconds, what we're seeing, this inhibitory effect, is due to synaptic inhibition via the GABA A receptors. If you want to know more about that, Charlie Stagg and I did a webinar about that a few years ago, and all its wonderful complexities. That is on YouTube if you want to look into it. I'm only explaining SICI here because SICI is one of the measures that's particularly well studied in terms of comparing fixed intensity and threshold tracking TMS. So the point of this webinar is to kind of summarize, as we currently see it, what is the best, in inverted commas, way to measure this inhibitory or facilitatory effect that the conditioning stimulus is having, and therefore what is the most appropriate way to use paired pulse TMS to measure the degree of the function of these inhibitory and facilitatory circuits in someone's brain, and how that might change with disease or with application of a drug. And there are two approaches currently. There is the fixed intensity approach and the threshold tracking approach. So the so-called fixed intensity approach, as I call it, is so-called because the intensity of the pulses we give stays consistent across the protocol. So to start off with, what we do is we calculate the resting motor threshold for the participant. So I put up a poll about that, and the majority of you seem to be familiar with the resting motor threshold. It's a universal measure that we use in most TMS studies of the motor system, where it's defined as the minimum intensity of the stimulus you need to give, so that 5 out of 10 of your stimuli will cause a response in the form of an MEP that has an amplitude of at least 50 microvolts. 50 microvolts is generally chosen as it's kind of the smallest kind of reliable size of MEP under some definitions. So in short, it's the stimulation intensity at which we expect to get a median response of 50 microvolts peak to peak amplitude in our MEP. So that kind of allows us to standardize across different people and determine what's the kind of minimum effective stimulation intensity in that person to engage a muscle response. So we calculate that resting motor threshold. The way that we calculate that is usually, as many of you will be familiar with, is through starting off at a stimulation intensity that we know evokes some sort of muscle response, and then applying, for example, 10 pulses, and for each pulse we look at, is the MEP bigger or smaller than 50 microvolts? And if more than 5 out of 10 are bigger than 50 microvolts, then that's too many MEPs. So what we do is we turn the stimulation down a bit, and then we do the same again. But if we apply 10 pulses at a lower stimulation intensity and we only get, say, 3 out of 10 responses above 50 microvolts, then we turn the stimulation intensity up again. And we iteratively turn the stimulation intensity up, down, until we hone in on or converge on the stimulation intensity, which results in 5 out of 10 responses being above 50 microvolts. So just, that'll be familiar to many of you, just keep that in mind. So when we have this resting motor threshold, or RMT, we then calculate what we're going to use for our test stimulus intensity. So that's the one that's going to activate the upper motor neurons. And typically, in most cases, it's supra-threshold, by which I mean it's substantially above the resting motor threshold. That could be 120% of the resting motor threshold, or it could be the amplitude that gives an average response of a certain big amplitude. But the reason we want to use a supra-threshold response is we want our test stimulus intensity without conditioning, when we just give it alone, to reliably, consistently produce motor evoked potentials, so that then when we introduce the conditioning stimulus, there's plenty of room for the MEP to either get bigger or get smaller and allow us to measure inhibition or facilitation. We then calculate what conditioning stimulus we're going to use. Now, for different types of measurements, we can either use sub-threshold stimuli, so ones that are not going to evoke MEPs because they're less than resting motor threshold. So, for example, in the case of sickie, we use about a 70% of resting motor threshold intensity. But for others, we might use a supra-threshold conditioning stimulus. That all depends on which measure. But for the sake of this, let's just focus on using a sub-threshold conditioning stimulus. So then we've calculated our test stimulus intensity, our conditioning stimulus intensity. Those are not going to change through the protocol. And then what we're going to do is record 20 data points where we just delivered the test stimulus and record how big the response is, and 20 test stimuli preceded by a conditioning stimuli at whatever fixed interval we're going to use. And we're going to measure the average MEP response to that. Now, I say 20 here, you can use 10, 15, 20, 25, depending on your specific protocol. You might use more or less, and I'll talk about that later. So you collect your overall 40 sets of data points. Now, in reality, you randomize them together. You wouldn't ideally do the 20 single pulse or test stimulus only ones first and then the 20 paired. You'd randomize them together. So you do that, and then you go home or you go back to the office and you have your data. You look through your data and you disregard any trials where the person is showing substantial baseline muscle activity. So any evidence that they are pre-activating their muscle based on the amplitude of the EMG before you've given the pulse. And that's important because if you pre-activate your muscle, you're going to get a much bigger motor evoked potential compared to if the muscle's at rest. So it's really important that the person is consistently resting. And then, as I said, we're going to get the mean of our amplitude response where we only gave the test stimulus, which we call the unconditioned mean amplitude. And we're going to get the mean when we applied the pairs of pulses, so which we call the conditioned mean amplitude. And then we plug it into this formula or small variations of this formula, which essentially tell us how much relatively bigger or smaller did the mean amplitude get when we added in the conditioning stimulus compared to when it wasn't there. So if I give you an example of what that looks like, say on the left-hand side at the top, we have an example of an EMG recorded when we gave just a test pulse. So the spike that I point to for the test pulse is just the artifact where we've delivered the pulse. And then we get this biphasic wave, which is our motor evoked potential. So we collect, for example, 20 of those. Then we record the average or the mean across those trials of the peak-to-peak amplitude. And say, for example, that's 100 microvolts peak-to-peak amplitude. Then we look at our EMG where we've applied 2 pulses, so the conditioning pulse and then the test pulse. So we have 2 pulse artifacts here, and then our biphasic motor evoked potential. And say we look at the average amplitude here, and it's only 50 microvolts. So it's about half of what it was when there was no conditioning pulse. So we plug that in to our formula, and what we see is that we get a value of minus 50%. So the MEP amplitude on average is 50% smaller. And that's what we quantify as 50% inhibition due to the conditioning stimulus. So in the case of fixed intensity TMS, negative values are inhibition, whereas if the MEP was to get bigger with the conditioning stimulus, we would end up with a positive number, and that would be facilitation. Depending on how you calculate this, the numbers might look slightly different, but generally smaller values mean inhibition, larger values mean facilitation has occurred from the conditioning stimulus. So this is the first paper where they defined short interval intracortical inhibition from Queen Square from 93. And you can see this inhibition. so where the mean amplitude has gotten smaller than in the absence of the conditioning stimulus, you can see this inhibition, so these values below 100 in this case, for interstimulus intervals of 1 to 5 milliseconds, which is our short interval intracortical inhibition. Actually, if you make the interstimulus interval longer, you start to see the opposite. You start to see facilitation, where the MEP gets bigger when you have the conditioning stimulus. So that's the basis of fixed intensity TMS. And why it's particularly of interest at the moment is that it's being used a lot to try and understand diseases that affect the motor system. So this is actually a paper from very soon after they discovered short interval intracortical inhibition, where they looked at this phenomenon in people with and without ALS, as well as spinal muscular atrophy. And what you can see is that you can see that nice robust inhibitory effect of the conditioning stimulus in both the healthy controls and the people with spinal muscular atrophy. But if we looked at people with ALS, the conditioning stimulus doesn't seem to be having nearly as much of an effect, indicating that this GABAergic inhibition that we're eliciting with the conditioning stimulus is not happening, or is happening to a lesser degree. So what are the benefits of using this fixed intensity approach? Well, the main benefits, at least to my mind, are that, first of all, it's very quick and easy to set up. So, it's pretty easy to just set your stimulator to these fixed intensities and apply X number of single pulses and X number of paired pulses. And it's also very straightforward to analyze the data. So you just take the data home, you can do it after the session, you separate the trials out into where you just gave a test stimulus or where you gave both stimuli, and then you calculate the average MEPs, amplitudes. So you could do that through some fairly straightforward coding, or even using Excel, or if you really wanted, you could do it manually. But there are a number of issues or kind of cons to this approach. So one would be the amount of time it takes, and the amount of time it takes relates to the number of trials you decide to use. So I gave the example of using 20 repetitions. And the reason I give that example is that anyone who uses TMS will know that motor evoked potentials fluctuate, not randomly, but with the changing excitability of the cortex, which naturally happens at rest. So if you apply the exact same TMS pulse to the motor cortex 5 times in a row, you're going to get 5 different size MEPs, because the cortex is always fluctuating in excitability to some degree due to your brain doing its job. So what we need to do in order to determine what the conditioning stimulus effect is kind of average out to kind of reduce the influence of that ongoing fluctuation. So we need to collect 10 or 15 or 20 pulses with and without conditioning, so that we can compare averages and therefore determine that the difference in the average size of the MEP is due to the conditioning stimulus, not due to just random or chance fluctuations in your cortical excitability. And the more pulses you use, the better your signal to noise ratio will be, and your estimation of inhibition or facilitation, but also the longer it's going to take, which is not always practical in a clinical context or in a research context. One of the other major issues is floor effects. So particularly if you think about inhibition. So inhibition is reflected as the average motor evoked potential getting smaller. But what happens if your motor evoked potential gets so small that it disappears? So in people with strong inhibition, what you're going to see in some cases is the average motor evoked potential you were getting with your test stimulus just disappears when you add in the conditioning stimulus, which means that you can certainly detect inhibition, but you are probably underestimating inhibition, because even if you for example, give a drug that enhances more and more and more inhibition, you're not going to be able to make the MEP smaller than nothing. So you're going to end up with this floor effect. So you're probably going to underestimate inhibition. And this is particularly a problem if you're dealing with small muscle responses to your test stimulus in the first place, which could happen in diseases like motor neuron disease. And then I just put this in as kind of, it's not necessarily always an issue with fixed intensity TMS, but most people, what they do is they collect their data, and then afterwards, when they go back to the office, they disregard the data where there's this background muscle activity. You can write some codes or protocols to disregard the trials where the person is pre-contracting their muscle during the session and then replace them. But what people will often do is just kind of try to monitor the person's relaxation during the session and then bin the few trials where they couldn't relax afterwards. But what you will see in papers is people saying the person just couldn't relax, and or we didn't account for it during the session, and then we had to disregard their data because there wasn't enough clean data afterwards. And then the last point I'll mention, but I'm going to go back to this later, is that some studies show pretty poor to adequate interday and intraday reliability, and I'm going to touch on that later. So let's go on to threshold tracking. So what is threshold tracking? So threshold is just a basic property of any stimulus response experiment in electrophysiology, which is the strength of a stimulus we need to give to get a specific probability of success, or and in our case, success would be a response of a certain size. Tracking means collecting stimulus intensity versus success data. So by success, I mean, was there or wasn't there a certain response? So collecting this data and then using it to identify the threshold and how it changes under different conditions. So if I just ignore the under different conditions thing for a second, this probably sounds pretty familiar to many of you who've never done threshold tracking for paired pulse. So if I plug in a few kind of example parameters here. So if I say the probability that we want is 0.5, so we want a 0.5 success probability. So we want to determine what stimulus do I need to get 50% probability of success. And then if I define success as getting an MEP of at least 50 microvolts, well, then you will recognize this as how we measure resting motor threshold. So threshold tracking, if you think about it, is like an extension of something most of you already do to measure resting motor threshold, which is varying the stimulation intensity to hone in on the intensity you need to give to get a certain response at a certain probability. So the whole idea of tracking is really born out of the work of Professor Hugh Bostock. So this was originally kind of described in the context of looking at motor axons and peripheral electrical stimulation. So the earliest of his papers that I could find was this one from 1988 that describes this in humans. So it was this idea of tracking the threshold of a motor axon by applying different stimuli to understand potassium channels. And then he applied it to look at the effects of ischemia on that threshold. So what happens to the excitability of these motor axons if I apply ischemia, and understanding that in the context of disease. So from this paper in 1998, this is kind of a nice overall summary by Hugh Bostock of the technique and its use in studying human nerves. And he says in this that what we're doing is comparing the resting threshold to the threshold that we see in the case of some change, for example, in the environment, or as might sound familiar to us, when we apply some preceding single impulse. So this is starting to sound a bit like something we would do in TMS. So if we put where am I? Yeah. So if we look at how that applies to TMS, so let's compare it to what we were doing a fixed intensity TMS. So again, we're going to calculate the resting motor threshold, similarly to what we would do in fixed intensity TMS. We're also going to calculate a fixed conditioning stimulus intensity. It's going to be either subthreshold or suprathreshold, much like we do for fixed intensity TMS. But what we're not going to do is fix the test stimulus intensity. What we're going to do instead is define what I said previously about thresholds, which is what is success. So we're going to define a target motor evoked potential amplitude. And if the MEP is bigger than that, we'll say that's a success. And if it's smaller than that, we'll say it's not a success. So essentially what we're doing is flipping things around, where before what we were doing was fixing the pulse intensities and looking at the change in amplitude. Whereas now what we're going to do is fix what we want in terms of amplitude and look at how we need to change the intensity to maintain that. So what we're going to do is deliver pairs of pulses, so our conditioning and our test stimulus. The conditioning stimulus is going to stay the same at whatever you calculated. But what you're going to do is change the test stimulus intensity. So usually you would start off with a test stimulus intensity that's somewhere close to what you expect the threshold to be. So you might set it near to your resting motor threshold. And the reason you would do that rather than starting off with a very low test stimulus intensity is that then you're going to have to just spend a lot longer inputting more and more data points before you get close to the correct threshold in this case. But if you start off using a test stimulus that's near to what the threshold is going to be in this case, it'll be quicker, simply. But don't worry about that too much for now. In the case of threshold tracking, it's an online analysis. So you're constantly collecting the data and you need to immediately determine if you've got a success or a failure, i.e. was the MEP bigger or smaller than your target amplitude? And then you need to input that information into some kind of algorithm which will recommend to you what stimulus intensity to try next to be more likely to get to your desired probability of success, i.e. your threshold. What's important about that is because you're doing this online analysis, you can't afford to leave in noisy trials and bin them later. You need to constantly be rejecting data that's not suitable for analysis and then replacing it. So you have to have built into your kind of online program some criteria by which when your EMG data is collected, it checks if the person had too much background activity, and if they do, bin it and do another trial to replace that. But let's presume your data is lovely and clean, the person's nice and relaxed. The way that threshold tracking works, much like for resting motor threshold, is if you find that your MEP is smaller than threshold, i.e. no success, you turn the stimulation intensity up. So you're likely to get a bigger MEP. And vice versa, if your MEP is bigger than your target, you turn the stimulation intensity down. Now that's the test stimulation intensity. The conditioning stimulus intensity stays the same. And you essentially turn it up and down until your set of rules has received enough information to tell you with confidence the stimulation intensity that is associated with a 0.5 probability of getting your target MEP amplitude. Now, how many data points you need in order to be sufficiently confident is still open to debate, and the exact set of rules you should use to turn the stimulator up and down and so on is again still being refined. I'll talk about that in a second. But it's all based on the same idea of, turn the stimulator intensity up and down until you converge upon a test stimulus that's associated with a 0.5 probability of getting a certain size amplitude. So in this case, the way we're going to measure inhibition and facilitation, and therefore the effect of the conditioning stimulus, is a bit different. So what we're going to do is look at how the threshold has changed relatively with the conditioning stimulus present versus when it's absent. So if we go back to our data, unlike with the fixed intensity TMS data, so the pseudo data I showed you, in this case, you can see that the motor evoked potentials on average will be the same size because we're looking at keeping the MEP amplitude consistent. But what we're looking at is the change in the stimulation intensity we needed to give in the presence of the conditioning stimulus versus in the absence. So let's say we just use our test stimulus, and in order to get an average response of, say, 200 microvolts, or a median response of 200 microvolts, we find that we need to use a 50% of stimulator output. MSO is maximum stimulator output. So we find that in order to get a median response of 200 microvolts MEP, we need to use 50% of MSO. But if we add in that conditioning stimulus, say for Sickie, it's a 70% or MT conditioning stimulus, all of a sudden we find that now we have to use much more stimulation intensity to get that size response. So we have to turn up the stimulator. And if you think about it in terms of inhibition, it's because we need to turn up the test stimulus to override the inhibitory effect or surmount the inhibitory effect that the conditioning stimulus is having. So it's a bit like back to front to fixed intensity TMS. So if we plug that into this formula, so 75 minus 50 over 50, we get plus 50. So the thing I want to emphasize here is that when you're looking at threshold tracking data, it's the opposite to fixed intensity in the sense that inhibition is seen as more positive values and facilitation is seen as more negative values, because you're having to turn the stimulator up to counteract the inhibitory effect. So, right. So where did this application of threshold tracking start in TMS? Well, actually, even though it's kind of become more known about recently, it started quite soon after the initial discovery of SICI in 1993. So in 1999, Friedman Avicius and Hugh Bostock and their colleagues looked at this in TMS. So they looked at how if you set a certain fixed strength of conditioning stimulus, for different conditioning stimulus intensities, how did this threshold change? How did this stimulation intensity you need to give to get a desired response change? And you can see, particularly if we look around a 70% conditioning, 70% of RMT conditioning stimulus, where we expect to see SICI, you see this big bump in the threshold where they had to turn the stimulator up much higher. So that's our index of inhibition. And likewise, the opposite would be facilitation. So again, this is particularly of interest in motor neuron disease. There have been a lot of studies already using the fixed intensity approach. But then around 2006, Vucic and Kiernan started looking at how could they apply this tracking approach to reinvestigate this. And again, they found that this inhibition was present. And then if they looked in MND, there was less of this inhibition. So the threshold wasn't going up as much as you would see in controls when you had this conditioning stimulus. On the right-hand side, you can see a lot there. This is just one example of work done by Hatashi Tankisi and Hugh Bostock and Martin Kolzenberg and others, where they have been developing this method. And I'm going to be talking a lot about their work in kind of refining further this approach to threshold tracking in TMS. So they and others and myself have consistently found that this measures impaired in ALS. If you want to hear a bit more about the work we did on that recently, I did a webinar on that as well. So what are these set of rules, or how do you use the data you're collecting to get the threshold? Well, there are two main kind of ways of doing that. So in 1999, Friedman Avicius, while working with Hugh Bostock, looked at this idea of using this so-called hunting. Sometimes you'll see it called threshold hunting, sometimes threshold tracking, where you use this logarithmic regression. So you're feeding the data into this logarithmic regression, and it's every time you input data, you get a new recommendation of what stimulus intensity to use. And I think the initial rule that they used was that once there had been recommendation of the same strength 6 times, that was enough data to use the model to define what was the threshold. But that has been subsequently kind of refined and updated, and there's a lot of data that has been collected to kind of look at improving or refining the best way to do that. So now Hugh Bostock has made that the software which does this all very neatly, and it's a lovely graphic user interface through the QTrack software, which Digitimer kind of market. The other kind of main way of doing it is the maximum likelihood through parameter estimation by sequential testing, or MLPEST. So Friedman Avicius developed this. Many of you may be familiar with this because this free kind of GUI is available for a lot of people use it for recording resting motor threshold. And it's simply a log likelihood function where you input what stimulus you used and whether you got a so-called success or failure, and it gives you the next recommendation, and so on and so on. And then it uses confidence intervals to define when you have sufficient confidence in your estimate of your threshold. So Winston Byblow and his team in Auckland used this GUI manually. So they had somebody manually inputting whether they got a success or failure, and somebody manually changing the stimulator output to do this threshold tracking. And And then myself and Richard Carson developed with Friedman Vicious a kind of automated version of this, where all you'd have to do is hold the coil over the head, and the data would be automatically read, and the recommendation would be input into the stimulator, so you didn't have to keep fiddling with the machines. So we've developed that, and we've published some studies using that. I think it's quite comparable to Q-Track, but it's not made up as it's not kind of a nice, refined, easy to use package. It's something I have to tailor for each lab, and so most people would opt for the Q-Track version. So why use threshold tracking? So some people were saying that the reason that threshold tracking was developed in TMS was to overcome the variability in the MEP amplitude and how that was affecting amplitude-based tracking or fixed intensity tracking, or sorry, amplitude-based TMS or fixed TMS. But that was not the case. And there's a nice quote about this in Hataji Tankisi's paper up top there. So the two main reasons that Hugh Bostock would cite is that it was to avoid the floor effects that were causing problems in fixed intensity TMS. And it was also to limit the contribution of spinal and peripheral elements to the measures. So the theory is that because you're keeping the size of the motor output consistent, the effects of the conditioning that you're measuring are more related to cortical changes, because the ultimate size of the motor evoked potential is not different. Now, that hasn't been kind of shown in a paper, but that's the theory behind it, and it kind of makes sense. So, as opposed to fixed intensity TMS, threshold tracking TMS can be a bit more tricky to set up, because you need to design these kind of online data processing protocols to perform the tracking and decide on rules to track. So that was an issue that I faced a lot when I was starting threshold tracking, but I will say now with Q-Track and so on, it is actually a lot quicker and easier to set up, because you can it's all kind of available to kind of purchase a license for the software and the hardware. So it is actually becoming easier. One issue that I have encountered is that you can have ceiling effects, where the threshold gets bigger and bigger and bigger with the inhibitory effect until you can't turn the stimulator up high enough to overcome that inhibition. And it's almost a bit like the opposite of the floor effect. However, I have only experienced this in a limited number of people, probably particularly because I use a smaller coil, which requires higher stimulation intensities. Whereas I haven't really seen that being mentioned as an issue in those who use bigger coils, the 70 BF coils. I just use a smaller coil because I'm trying to fit multiple coils on the head at once. But I think it's a limited issue. The advantages are it's a lot quicker. You need to use less trials to get sufficient confidence to determine your estimates of the threshold. Because you're using this online tracking, there's no risk of losing data after the session because it's too noisy and so on. You have to use it because of the nature of the protocol. There's no floor effects, so that's the massive one. It's been shown that it has much superior intraday and intraday reliability, which I kind of alluded to earlier being a limitation of the other method. So to kind of expand on that, I just want to point to the work of Ginta Samisite and Martin Kolzenberg with Hugh Bostock and John Rothwell. This is a really nice paper. It was the first one to like directly compare the two. And one of the key kind of demonstrations from it was that threshold tracking provided much superior intraday and intraday reliability compared to what it's called ASICI in this paper, or amplitude-based SICI. So here they're comparing the degree of inhibition using the two methods. I use fixed intensity. Some people use amplitude-based. It's either way, ASICI is when I say that I mean using fixed intensity TMS. And then there's a nice discussion in this paper about the way that this method allows you to avoid floor effects. There's a lovely figure at the end of it. But there is a discussion in there around the idea that if you're keeping the test stimulus consistent using amplitude-based SICI or fixed intensity, the assumption is you're consistently activating the same set of motor neurons, which might be preferential if compared to threshold tracking, if you're interested in specifically studying the same pool of motor neurons. But the issue with that is you're going to get floor effects, because if you're not expanding the pool of motor neurons you're looking at in accordance with the amount of inhibition someone's showing, you're going to end up with floor effects where you've completely inhibited that pool of motor neurons, and now you're underestimating that person's inhibitory potential or inhibitory function, which is particularly problematic if, for example, you want to study how a disease or a drug affects inhibition. And notably, there was a strong relationship between the two measures, so they do seem to be largely capturing the same thing. But there was much, because of the improved interclass correlations, it seems that you would need to use a smaller sample size to get sufficient power for these studies. So that's obviously important, for example, in early phase clinical trials, if you're picking between the two. So then there's a bunch of great studies by Hashi Tankisi and the same group and Hugh Bostock, where they're looking at now refining these different approaches. So here in this study, they looked at amplitude-based SICI or fixed intensity TMS recorded SICI versus two different types of threshold tracking, so-called parallel and serial. So in the early kind of motor neuron disease studies using threshold tracking, they were using this serial threshold tracking. So what they would do is look across all the interstimulus intervals at which you get SICI. So 1, 2, 2.5, 3, and so on. And to kind of speed things up and for efficiency, it was designed so that first of all, you'd get the threshold at 1 millisecond. And then rather than resetting the algorithm, you would start off at that same stimulus intensity, whatever your threshold was for 1 millisecond. And then starting there, you would change the stimulator intensity to try and get the threshold for the next interstimulus interval. So say 1.5 milliseconds, and so on and so on and so on. So you weren't starting back at the same test stimulus each time. You were using the threshold of the previous measurement as a starting point for where you were going to go with measuring your threshold for the next interstimulus interval. Whereas parallel tracking, which is now commonly used, is where you essentially measure all the different interstimulus intervals independently. So there's no potential that one can influence the other. You set your test stimulus intensity for all measures at the same starting value. So you're not leading potentially the algorithm towards whatever the value of your previous measurement was. And when they did this comparison, you can see that the amplitude-based SICI, or the fixed intensity approach, and the parallel threshold tracking approach, the blue and the green, gave very similar measures of SICI. But this serial approach was dramatically giving more greater values of SICI. So what they did was they thought, is this because every measurement taken is more similar to the previous threshold recorded because we're not resetting the initial test stimulus value? And that does seem to be the case. So what they did to test this was they did this serial tracking starting at 1 and then going 1.52, 2.53, so on. And then they did the reverse. They, in the same people, measured SICI, but starting off at the higher end. So at 7 and then going 7, 6.56, 5.54. And you can quite clearly see that there is, for the ones that started off with the lower ISIs or interstimulus intervals and went up, all the values were higher. They were all biased towards the first value. Whereas the opposite was true if they started at the lower end. So if they started at a 7 millisecond interval, all the SICI estimates were lower. They all seemed to be pulled towards the initial value. So it seemed to be essentially smearing the threshold values or biasing them across the interval. So it's really important to avoid such a bias if you're looking at doing a study across interstimulus intervals. And just to note also in this study, there's actually a bunch of very helpful information in this paper about approaches. But one thing to note was that they checked the effect of age on the measures, and they found, consistently with other fixed intensity studies, that age, those of higher age had less amplitude-based SICI or fixed intensity SICI, but that age effect didn't seem to influence any of the threshold tracking measures. So again, if you're using fixed intensity TMS to study sickie, you should consider the effective age. It seems to be more of a bias if you use fixed intensity TMS. In terms of the number of stimuli you use, a bit like I mentioned for fixed intensity TMS, there is kind of debate around, how many stimuli you should use to inform your algorithm to determine the threshold. Obviously, the more you use, the more confidence you have, but the more time it takes, and that's important for things like clinical trials or recording in clinic. And at a certain point, the more and more data you collect, you're not really meaningfully adding any benefit. Now, this is a nice study, again, by the same group, where they compared 6 versus 10 stimuli. And notably, for the fixed intensity approach, they found that reducing the number of stimuli used from 10 to 6 dramatically and significantly expanded the variance of the measures, whereas that variance didn't seem to expand nearly as much if you use threshold tracking. So threshold tracking seemed to be more kind of provide greater confidence at a lower number of stimuli. Now, I will say this is in healthy controls. So in people with disease, you're going to have more variation in MEPs, and the cortex's activity can be less predictable. So I would recommend using more stimuli in certain disease cohorts. But again, that's something you could test in your pilot stages. And then finally, talking about coil shape. You probably know if you use a circular coil, you activate quite a large area of the cortex, and so you're quite non-focal in your stimulation. Whereas if you use a figure-of-8 coil, the area of peak stimulation intensity is quite small and quite focal. The advantage of using a circular coil is that you can skip essentially the hot spotting or the step at the start where you have to determine exactly where to put the coil. So it's quicker, but it's a lot less focal than using a figure-of-8 coil. But this is a nice study looking at using the two types of coils in a threshold tracking context. And the data suggests that it is better to use a figure-of-8 coil as well as it causing less incidence of lack of inhibition. Now, this is in healthy people. It also is associated with less discomfort. So that's just an interesting paper. Obviously, there's a trade-off with the time for hotspotting, but it's some nice data there. And then, as I said, I've already mentioned that the coil size is also important. The smaller the coil you use, this can be important if you need to fit multiple coils on the head, particularly if you're delivering your conditioning stimulus to a different area, which is not the case in sickie, but is the case in other measures. You just physically can't fit 2 big coils on the head at once. But if you are only using 1 coil, I would recommend to use a larger figure-of-8 coil, because then your thresholds will be lower and you're unlikely to hit that ceiling effect that could happen. So to wrap all that up, fixed intensity TMS, very straightforward to implement, but subject to floor effects. Threshold tracking TMS can be complex to set up. I say again, that's becoming increasingly easier, but it has better reliability and no floor effects. If you're using threshold tracking TMS, the rules by which you perform this tracking need to be carefully considered depending on who you're studying, the disease cohort, etc. And really, if we're moving towards clinical applications, for example, using these as diagnostic tests, we should try and work together to converge upon a consensus as to what is the protocol that we should use consistently across sites. And figure-of-8 coils are preferable, but more time-consuming to use compared to figure-of-8 or circular coils. So that was a big one. I hope I haven't bored you all. So thank you very much for listening to that. If you are interested in electrophysiology, I am going to be shortly advertising for a postdoc for a funded postdoctoral position for a few years. So if you are interested in EEG or MEG, and you have some coding experience and signal analysis experience, please email me. I'd be delighted to hear from you and tell you more about it. We have a lab website, the mcmackinlab.com, where we have lots of information about what we do and who works in our team. And here are just some pictures of the lovely people who work with me, who are all incredibly talented. So if you're interested, we'd love to hear from you if you'd like to work with us. And thanks very much. And I'd be happy to take any questions.